access to, and we will introduce the indoor positioning system, which has been released on this Huawei's phone. Yeah, because this part previously Ariel will introduce this part, but because of some urgent reason, he cannot participate in this tutorial. So I will represent him to give this tutorial. But both of us are from the same team and responsible for indoor positioning. Yeah. Okay. Yeah, I'm very glad to introduce some of Huawei's latest achievements and technologies in indoor positioning research, which has been put into commercial use in Huawei's latest product, Mate X2. In this section, Dr. Guan and I will introduce the following three aspects. The first one is that I will briefly introduce the indoor positioning system on Mate X2. In the second part, we will briefly introduce how to generate the fingerprint database, some problems in indoor positioning, and some solutions provided by Huawei. And from my side, I will introduce fingerprint degradation, noise in Wi-Fi scan, and then Dr. Guan will introduce two latest researches. And finally, Dr. Guan will give a future vision. Yeah. Okay. Let's go to the first section. On April 28th, Huawei had a new product launch event and unveiled the industry's first 3D precision product, Huawei Mate X2, which is a folding screen phone. At the time of release, it covered more than 160 cities, more than 1,300 shopping malls, and more than 20 airports and railway stations in China. And currently, the number of supporting shopping malls has been up to 2,200, and the number of airports and railway stations has been up to 50. The indoor positioning system implements indoor store level precise positioning and can switch the floor automatically according to people's position. And it can provide continuous position results. Now let's watch a video which compares the Huawei's latest Mate X2 and iPhone 13. This map is for Wanxiang Tiandi in Shenzhen, China. From this video, we can see we can see that the position result from Huawei's phone is continuous. And when the person go to the escalator, we can see it can automatically switch the floor. But we can see there's a lot of jumping points in iPhone 13. And it needs to change the floor manually. Yeah. And in the third floor, we can see the result is still continuous. But in iPhone 13, we can see there are still a lot of jumping points. Yeah. So how can Huawei implement so good position results? As we know, there are many methods for indoor positioning, but these methods often requires additional hardware deployment. And this brings high cost and is not conducive to large-scale commercial use. To achieve large-scale commercial use, we use a fingerprint-based zero calibration solution. Fingerprint-based indoor positioning requires training the fingerprint library in advance. When positioning is performed, the location of the point is determined based on the similarity between the location point and the point in the fingerprint library. Therefore, the core work of the fingerprint-based positioning algorithm is how to obtain such a fingerprint library. In current commercial solutions, fingerprints are collected manually in advance. However, fingerprint is aging. It means that with the time goes by, maybe the fingerprint will be old and we cannot use it anymore. So the maintenance costs are very high when the number of buildings is very large. To address this problem, Huawei proposed its own solution, which is called self-learning 3D fingerprint library construction. This algorithm consists of two processes, namely 3D and 2D. Yeah. The 3D part mainly addresses the problem of data height, that is data layering. We need to get the layering of the data. Yeah. And also we need to know the relationship of the different data. So the 3D part consists of two parts, which is elevation detection and elevation clustering. In the 2D part, we mainly deal with everything related to 2D positioning. In this part, it consists of two subparts, which is Wi-Fi scan clustering and Wi-Fi fingerprint coordinate alignment. Okay, let's look at some more detailed steps. In 3D section, we first need to detect the elevation of the data. Elevation detection deals with how to detect based on the different available information, such as parameter or IMU. Yeah. Noise and outliers must be filtered during this part, and we need to make sure that the detection is accurate, because inaccurate elevation can be significantly affect the final floor accuracy. After the elevation detection, we need to cluster these elevations. After the cluster these elevations, there are some high density elevation and still some low density elevation. The high density elevation can represent the height more accurately, but the low density elevation may be an outlier. So we need to use these outliers much more carefully. Yeah. In 2D section, our goal is to get the location information of each data. Based on the Wi-Fi information, we calculate the connectivity between different data and cluster these Wi-Fi points. However, after we get connectivity between the Wi-Fi points, we still don't know the location of each point. So we need to coordinate these Wi-Fi points. This process is an optimization process. So we need to build an objective function based on the Wi-Fi connectivity and calculate the optimal location for each point. The above is the main process of fingerprint library training. In the next step, we will introduce some common problems or issues in the whole algorithm. Yeah. The first one is the Wi-Fi scan noise. As we know, because in different shopping malls and at different times, the user density is constantly changing. So it affects the signal transmission. As a result, even in the same location, the scanned Wi-Fi strength maybe changes at different times. In addition, because the shopping malls internal structures is also different. So as a result, the distance may be different between two different Wi-Fi points, even the Wi-Fi changes is the same. The next problem is the aging of the fingerprint. Yeah, after we training the fingerprint library, maybe some shops will maybe added, some shops may be closed, routers may be replaced, and areas may be changed. All of these maybe cause the aging of the fingerprint database and inaccurate location. Therefore, we need to consider how to update the fingerprint library. The third issue is the impact of noise. As we know, when we collect the AP, which is access point, there are a lot of mobile APs. And in our test, we found that the mobile AP could reach about 25% to 40% of the access point with just one Wi-Fi scan. What's more, fixed access point will also change, such as with changes of shops, the AP, access point relocation may be changes. Another one is the AP replacement. In addition, if high security settings enabled, MAC address will also be rotated. So this is the third problem. And the first problem is the noise of the parameter, which can cause the false detection of elevation. Some noise may be produced by the enclosed areas, and some noise parameters may be caused by the sensors in different devices. So in order to solve these problems, we propose some solutions. The first one is for the aging of the fingerprint. When the fingerprint library is well trained, the position accuracy is usually good. But with the aging of the fingerprint library, the position accuracy maybe decreases. Different buildings tend to aging at different speed. We need to be able to detect the aging of the fingerprint database. The first, we need to detect the aging of the database, and then we need to update the fingerprint database timely. We do not want to replace the entire fingerprint library, but we need to change part of the aging of the area. Also, we want to keep more fingerprint libraries of good quality and update just these aging areas. So our strategy is to retain the fingerprint database with new data and compare it with the aging fingerprint database. When it is detected that access points is in some areas change greatly, the new fingerprint database is used for replacement. Okay, the second solution is for the noise in the access point. As discussed previously, differences in access points is more significant in public area, such as shopping malls. Especially in commercial use, the number of access points with a scan could be very large, to about 200. But even though this does not happen in all cases, but it is frequent enough that this is not an outlier. Among such a number of access points, there are a certain number of noise access points. We need to filter these access points. One way to do this is to use the NLP, which is called natural language processing. Some access points has an access ID that is the name of the access point. We can get some information from the names of these access points. The mobile IP is type of access point that needs to be filtered. The name of this type of access point usually has some features, such as personal names, and like Jackie, or possessive keyword like Jack's iPhone. A fixed access points are one type of access point. We want to reserve as many this kind of access points as possible. And this kind of access point also has some features, such as the location name, like Zura. This is a shop's name. And other common keywords like guest or employees. The detection itself is good, but there are lots of SSID that are not recognizable because we know somebody may be given SSID very simple, so we cannot use the NLP to detect it very accurately. Yeah. So to solve this problem, we also use another algorithm called graph neural network, which is said GNN. It is based on the connectivity between the access point during scans, Wi-Fi scans. Access points that are found in the same scans are connected, and this creates connectivity between the different access points. And the community, and then we perform the community detection to connect the access points, and we will find that some access points are clustered very well, and there are some access points cannot cluster very well, and it means that it is an outliers. So we called this access point cluster very well as good AP, and the access point that cannot cluster very well, we call it is a bad AP. So we can filter out this bad AP. Yeah. Okay, this is two solutions from my side, and the next, Dr. Guan, we will introduce some other solutions generate the fingerprint. So let's welcome Dr. Guan to give an introduction for the next part. Yeah.
Thank you, Dr. Tao. Can you hear me? Can you?
Yes, I can hear you.
Okay, can you see my screen now?
Yes.
Right, okay, cool. Okay, let's start. Okay, then welcome to the third part of the second part of the tutorial. So thank Dr. Tao and also Dr. Wang and Dr. Huang for their parts of the tutorial. A bit of myself first. I'm Ren Guan. I have been working on indoor positioning and related topics for a while since I joined Huawei in 2020. Prior to that, I also read my PhD degree on the topic of crowdsourced indoor positioning in the UK. And at present, I'm with Riemann Laboratory, 2012 Laboratories Huawei, together with Dr. Tao's department and also team from our Edinburgh Research Institute. We delivered the first generic and Wi-Fi fingerprinting-based indoor positioning service earlier this year to Huawei mobile phone users. So behind this service comes with smart design and also hard work from our team, both from our researchers and also engineers. And also this is my third time coming to IPN conference, and I saw a lot of friends from the online audiences. And it is, yes, and it is still, it is really my honor to be able to give this tutorial. And Dr. Tao just shared the engineering challenges he and his team came across. For my part, we approach fingerprinting based indoor positioning problem from a more theoretical perspective. So our method is built around Gaussian processes, or GP for short. So to begin with, there are many existing solutions to Wi-Fi based indoor positioning. Firstly, we have this log distance path loss model. And the distance to loss model basically maps an absolute signal space difference or signal attenuation to an absolute physical distance. However, this model is just basically just too monotonous for indoor scenarios where attenuation is not just determined by a distance, but also many other factors that are not described by this model. So in practice, no one is using this model, but we list it here for completeness. Also, a learned log distance model can hardly be reused in another building without any extra feeding. And then we have KNN, or K nearest neighbor. I guess a lot of our audiences must be very familiar with this approach. It's the most straightforward approach to indoor positioning. So basically, you map a fresh fingerprint to the location that is closest or nearest in a signal space from the reference fingerprints. Many actual projects also used KNN for positioning directly. But from the learning perspective, KNN essentially has to memorize all fingerprints, or raw fingerprints, and it does not learn any transferable knowledge. In other words, if you try to position or map a new fingerprint from another building, you need to have fingerprints collected from that building. And finally, we have Gaussian process, or GP. GP-based approaches. GP basically optimizes the hyperparameters to its kernel to learn the correlation between nearby fingerprints. And it generally outperforms KNN and log distance path loss model, at least for our practice. GP outperforms the other two methods. So before we further explain GP, I need to walk our audiences through one basic assumption or one basic underlying model, which we called the chessboard model. Assume the area of interest can be organized as a chessboard with multiple rows and columns. On this chessboard, a smart device can report the received signal strength measurements or any other signal measurements from different Wi-Fi access points or different signal sources. At each grid, the RSSI follows a certain probabilistic distribution, of course, with a mean and variance, and we assume normal distributions. Say if X is the location we want to figure out, and then Y is the signal measurement, then Y equals Fx. F is the propagation function of the Wi-Fi signal. And then the indoor positioning problem becomes, given Y, can we calculate X? Say if the X is the problem we are trying to solve, then the underlying F function actually dictates how location affects signal measurements, or how X affects Y. And then eventually the problem becomes, given Y, can we get X? And also with fingerprinting, we assume we have collected a set of X to Y pairs. And then the problem becomes easy. So we formalize the likelihood of observing signal Y at location X as the conditional probability P of Y given X. We assume it is normal. We assume the conditional probability is normal. And given the mean and variance of each grid, we can calculate the conditional probabilities. So in the end, to position, that is to solve X, we maximize the posterior probability by choosing the correct grid represented by M and N, the index of rows and columns at the bottom right-hand side. So in other words, we want to pick the grid that maximizes the conditional probability. And this should be easy to deduce with Bayes' theorem. And that's our basic model behind our problem. And under this probabilistic framework, the positioning outcome hinges on the construction of the radial map. So the radial map, the radial map refers to the means and variances of all these of the distributions across each grid, which can be represented quite easily by matrices like this one, or tables like this one I shown here. And once again, the fingerprinting positioning problem can be now solved by learning the means and variances across all grids and all access points. So now the problem becomes, how can we get this radial map or the means and variances from the surveyed fingerprints? Intuitively, we know fingerprints collected nearby are more similar. So if two fingerprints are collected from two positions, positions that are far away from each other, then the fingerprints are not going to be similar, and vice versa. You may wonder how to quantify nearby and similar. They are in two different conceptual space after all. So nearby is a description in physical space, usually measured by distance in meters. And signal similarity is a description in signal space, usually measured by ISSI in our case, and also in decibels. So that's the actual role Gaussian process are playing over here. That is to measure how nearby is nearby and how similar is similar. And there are two other issues as well. So when we collect fingerprints, or the location of the reference fingerprint are highly arbitrary. So they could be from anywhere. They are not sampled from in a grid fashion, usually. However, we need predictions at regular placed grids if we want to use the chessboard model. So we want to cover the entire chessboard. And also, fingerprints have higher correlation if they are spatially closer. And what GP does is that it captures this intuition with its kernel design or covariance matrix design. How can we quantify nearby and similar? So that's what GP does. GP quantifies the spatial to signal correlation by optimizing the kernel or the covariance matrix with reference fingerprints. There's a time and IP limits. I'm not going to go into much details of GP, but right now let's see a demo video of how GP walks through one simple question or a toy example. So normally with GP, we have two parts. For the first part, we have to reconstruct our radial maps from reference fingerprints. So these reference fingerprints are collected from arbitrary positions, and they are rather scattered around the space. And then GP can be used to build a radial map as shown in this demo. And also GP can predict areas that are not surveyed. And additionally, the radial map does not expand as we have collected more fingerprints. So these are the two advantages that GP enjoy. And for the second part, we can use the radial maps to position. So this is a rather simple application of Bayes' theorem. So we have multiple radial maps from different access points. For example, if we observe some very strong signals from one specific AP previously, then the GP will regress that to a heat map, sort of heat map, and then tells if you see a new fingerprint based on the radial map from that AP, where it is likely to be positioned. And also we assume each AP is independent to each other. And then the position or the maximized posterior probability is indeed by solved by multiplying the posterior probability from each single radial map. And then as can be seen here, as more and more APs got involved in the positioning, the accuracy becomes higher. And the red dots on the bottom row shows the ground truth position, and the red dot shows the predicted location. So to compare Gaussian process to KN for one trajectory. So the first row shows the results, positioning results of the KN method. And the second row shows the results of Gaussian process. Gaussian process alone is clearly more stable and has a higher mean accuracy in the end. Similarly, for a second trajectory, we can reach the same conclusion that GP outperforms KN. So on average, GP has an improvement of around like 10% in mean accuracy. And also it's faster during the positioning stage compared to KN. Right. And as for GP implementing GP, they are, sorry about that, we don't have much time to go into the details of GP, but there are very rich online resources that we would like to recommend. For example, the GPyTorch, a torch-based GP library, and also Scikit-learn has native GP support as well. Additionally, GP is an old topic, but it's been developed over the years. This year, Neuro IPS or NIPS also includes a GP-themed workshop. And finally, you can't miss the classic textbook, Gaussian Process for Machine Learning, if you want to become a master of Gaussian process. Right. So this is the work from our last year's IPM work. So many people in our fingerprinting community would use GP to describe the uncertainty of fingerprints, or they basically use the covariance to measure the uncertainty of fingerprints. But from last year's work, we found that this is incorrect. And for more details, please refer to our paper from last year, from IPN 2021. And we found that measuring uncertainty in signal fingerprinting only with Gaussian process is incorrect. So in short, the variance of the predictive distribution of Gaussian process consists of two parts: the spatially varying parts marked by the red parts, red block, and also the spatially invariance term marked by the green rectangle. So the green rectangle term is a fixed term by definition and is learned by optimizing the log likelihood of observing all signals. And then the red rectangle term is spatially varying, but it does not depend on signal observations. And this term monotonously increases with the size of surveyed fingerprints and indicate surveyed fingerprint spatial coverage in general. So that's not about uncertainty, instead it's about coverage. As a result, although GP gives idiosyncratic variances, the predictive variances have nothing to do with signal uncertainty. So we argue that this is a common mistake in our community, in the fingerprinting community, that people take GP predictive variance as signal uncertainty. Okay, then what should we do? We build deep GP essentially by stacking 3 layers of GP together. Once again, like more details can be found in our paper, and I'm going to show the results here only. So we simulated signals sampled from Gaussian distributions based on the chessboard model introduced earlier. The signal source is isotropic, and the signal attenuates faster when closer to the source, as many may would have expected. And then the signal source, or the ground truth means, and also the ground truth variances is isotropic. And then the signal attenuates faster when closer to the source again. And take the AP located in the center points of the chessboard from our simulation as an example, as shown here. The predicted variance by GP stays almost the same, the yellow one in the bottom row in the middle. The yellow one is the predicted variances by GP alone. It stays almost the same across the whole chessboard as the data coverage is even. On the contrary, Deep GP predicts better variances as close, much more similar to the ground truth variances. And also, we have our latest work with GP and generative adversarial network is also accepted by DCH IPIN and will be presented in the afternoon. And also welcome to join our discussion and our afternoon presentation in room B this afternoon, yes. And in short, we learn how to use fingerprints collected from other buildings and floor plan to help further improve the positioning accuracy. Because since we have launched our indoor positioning services, we have collected and we have to manage a huge amount of massive corpus of fingerprints. Can we make use of fingerprints that are collected from other buildings to help positioning services in this building? I guess is an untouched problem within our community. So you can see how we dealt with this problem in this year's paper. I think you will find it very interesting. And as for the future, we believe there are 3 points worth paying attention to. Firstly, we need to mix physical models and neural network-based approaches or data-driven based approaches so that our networks have better interpretability. So we can better understand what's going on inside the network because it's based on physical models and it's related to, for example, distance and how signal propagates. And secondly, we have seen many works that extend the Wi-Fi positioning to motion sensing too. I think this is a very promising direction. And we have verified many of these new systems and found very positive results. For example, we have found wider works from Tsinghua, very useful in many cases. That is to use CSIs to channel state information from the Wi-Fi signal to sense how humans behave. And we have reproduced part of their works and found very interesting and positive results. And finally, we need to investigate new signal sources and more powerful models, for example, 5-time measurements, FTM, and also, as I mentioned, channel state information, CSI, and also millimeter wave radar. And then we can also apply more powerful models such as generative models to our fingerprinting problems. So I'm going to show some extra demos over here, because within Riemann Laboratory, we have developed many cutting-edge positioning technologies, some of which can be shared with our audiences, while some of which have to be kept as secrets. So for now, just for now. So I will end my tutorial with these 2 extra demos. The first one would be the non-VPS visual-based positioning, dependent positioning and navigation. And then the second one is lightweighted VPS dependent positioning and navigation. And enjoy the demo. So this is basically showing that we are generating pseudo point clouds from RGB images. by extracting feature points from the images we have taken using a mobile phone. Then as we accumulate more data, we can see we are building a whole building level point cloud based library. And then with that, we can do very interesting positioning and navigation applications. And then that shows the result from outdoor positioning. Fused with GPS positioning, I guess. And then some AR, VR applications. And then an application of navigation. Can also plot kind of a paddle path onto the video screen of the user to guide the user to the destination. And then it switch to indoor positioning from outdoor positioning. With text to indicate where to go. Right. Okay, that's the first demo. Then the second demo. Okay, this is fusing the this is fusing the GPS and the inertial measurements to do better positioning and navigation. And again with AR applications. And then again, since we don't have GPS indoors, we use Wi-Fi positioning, Wi-Fi based positioning. And then again, fused with PDRs, pedestrian dead reckoning, using inertial measurements indoors. Well, as can be seen here, if the user is holding the phone in a relatively fixed position with our PDR, you can basically reach maybe meter level, up to meter level accuracy indoors. Right. So finally, we are also recruiting newly grads, researchers and engineers for our 4 Chinese offices in Beijing, Shenzhen, Xi'an, and Wuhan. We also have offices in Germany and also Russia. So if you are interested in navigation, map building, positioning, wireless sensing, 3D construction, or even just machine learning in general, feel free to drop me an email via guanran@huawei.com. And thank you very much. This is the end of our tutorial.
Okay, thank you. Thanks, Dr. Wang and Dr. Huang, Dr. Guan, and Arif. Thanks for your wonderful report. Any questions from the audience?
Actually, I got a question from Nita Su. And his question is, NOS identification is a challenge to indoor positioning. So does carry face solve the problem of synchronization, or just enlarge the multipass problems? So my answer is, for this one is NOS identification, sure, need algorithm to do that. As mentioned in our standards, Huang Su said that our algorithm has solved the problem that can identify the correct ratio can be up to 98%. So almost all the just channels has been correctly identified. But that's in the simulation. Some algorithm like to evaluate the variance of the power in different antennas, for example, in that way. Another one is using AI machine learning to identify the NOS. This has been verified in our standards to be feasible. For carry face, actually, there are many imperfect factors, actually, like that. In addition to delay, is also very sensitive to the phase. Actually, is even more sensitive to phase in such case. So such synchronization errors can degrade the performance. But as we mentioned in our just simulation as well as the test bed, we're using a reference point so that the reference point send the sounding simultaneously with the target UE. So in that case, the imperfect factors at the 0B are almost exactly the same. Then we're using differential DPDOA can well consider the imperfect factors. So this is my answer to Nita Su.
Thank you.
Okay, hope it's yeah.
That's clear. Thank you.
Yeah. Yeah.
Another question from the audience. What is the best accuracy of the solution? Is it already considering unloss and harsh environment?
Is that a question for fingerprinting based indoor positioning? If so, then in our case,
yes.
Okay, right. Then in our case, if we survey the area well enough, we can reach like around 5 meters, But that's highly situational. That depends on a lot of factors. For example, how popular the building is and how dense are the AP deployments. And also, we can also improve the accuracy by fusing PDRs. Does that answer your question? And also, we don't discriminate and loss from loss, yeah, because it's fingerprinting. And right, and also I got a question from Xu Jiaoshou, Professor Xu. We are I think we have not formally met before, but Riemann laboratory has a great amount of collaboration with Professor Xu before. And then he asked me this question. What's your view on modeling the spatial connectivity by Kruging and by GP? How rigorous we can assume the PDF of the ISSI is Gaussian? To answer the second question first, we know that the PDF of the ISSI is not Gaussian, but we can't do any better. We can't do any better because Gaussian is simple and straightforward in terms of modeling. And then for the first one, to be honest, we don't think Kruging and GP share many features or essentially share the same idea. And personally, I don't think neither of them will be the ultimate model for indoor positioning, because they try to model the connectivity in a global way. That is to say, the correlation between signal and then the physical space is a fixed value across the entire grid or across the entire chessboard, which is not true. Which is not true in our practice. So we believe we need to have more powerful models. That's what I said in the tutorial. We need more powerful models that are spatially varying, that can detect at least like in patch by patch fashion or in a grid by grid fashion, that can predict and that can be dynamic enough to capture this kind of correlation in each grid, in each position and location. Yeah.
Another question from Professor Lee. The question is, printing, or do you have to resurvey the area? It's also for fingerprinting.
Oh, right. Okay. How do we update the database? And how quick can you resurvey the area? So in fact, that's not a matter, or it is a matter from the technical perspective. Then we of course, we fuse some of the data collected from our users so that it can be from beta user only, so that it can help with our decision making when we have to update the database and when we have to resurvey the area. And as for how quick can we resurvey the area, it depends. It depends on the buildings. Some buildings are very dynamic, then we have to maybe resurvey the area more frequently. Yeah.
Generally 1 month or half a year.
That's highly situational. I can't tell you a specific number. Right.
Yeah, maybe I can answer this question. Yeah. Currently, in our survey, we found that maybe for some buildings, after half of a year, is still very constant and have a good position results. But for some buildings, maybe 3 months, or maybe we need to update the fingerprint. So it depends on the building.
Okay,
yeah, actually, within 1 month, it is still constant.
Okay. Any other question from the audience?
Thank you very much for the presentation. Very nice presentation and a lot of very useful information. And I have a question about the 5G, about the synchronization. So is there any details about how to synchronize the base stations to make sure the indoor positioning can reach, say, summit level or centimeter level?
Yes. Okay. I guess we have the solutions from the standard as well as implementation, right? So one from standard is currently we have the define the reference unit. The reference unit can send some signals. So to calibrate the synchronization error, because the reference unit has a perfect null location there. So you can directly, according to the TDOA measurements, and then you can calculate what's the error between the zeroed bits. And this one has been finished in release 17 because we have the reference unit as like the UE or zeroed B can, or either zeroed B or UE can take the reference unit. This is one. And from the implementation, this depends on the vendors how to realize it. I guess I'm not sure you are from vendor, but basically you can. Are you from vendor? Sorry?
No, I'm from university.
Oh, from university. Okay, good. Actually, for implementation, actually, sometimes like depends on the architecture, and some architecture may have normally has the BBU or RU such in architecture. If they share the same oscillate, actually the delay between the different chains maybe is small. So I mean the synchronization has been very good, but also need some calibration there. That's fully depends on the implementation. So how to calibrate the error internally and how to design the oscillate there. Another one is even in some cases, like in our just the presentation, we still use the reference unit. That means we have calibrate UE to estimate some errors, can estimate the errors like the synchronization error, as well as the phase error there. So I still again highlight the phase is more random than the delay, because phase, the initial phase has jumped from each just the switch on off. So in that case, we have to estimate the error very accurate. Also, PDOA is more sensitive to the phase error, but phase error is no problem for TDOA based positioning, you know. So in that case, so I guess has present something in our presentation. Maybe in the future we will we try to just write some papers to exposure some details as more as we can, because this is related to some product, some solutions we cannot expose the very detailed. So, but currently we just say is based on our offline data analysis and some standards. So we try to just make it independent with product solutions. Okay.
Yeah, thanks, Dr. Wang. By the way, so my name is Bing Haoli. I'm from University of New South Wales. I'm also part of the steering committee of IPing. Thank you.
Okay, thank you.
Okay, Professor Xu.
Can I have
yeah, we still have 5 minutes.
Yeah, I worry I have too many questions. So because this is very interesting presentations. For Dr. Tao, so you mentioned about that a lot of APs are very unstable. For example, it could be hotspot as such. So like in your filtering process, do you heuristically identify those? I mean, like, do you set up some heuristic rules to identify what AP is stable, or like you have a network automatically to classify what is reliable, what is not reliable?
Yes, yeah, we have some algorithms to detect this noisy AP, such as introduced in the slides that like NLP or GNN. In NLP, we can detect the names of the access points, because we can get some information from the names of the access points. Yeah.
Thank you.
So we can, yeah. And if we use a graph neural network, we can use some community detection to detect which access point is an outlier and which one is a good access point. So we can use these methods to detect these access points here.
That's good. Thank you.
Okay, for the presentation, I think we will upload the presentation after we get the authorization from the speakers. Any other question?
Yeah, can I ask like a very generic question? So for indoor, oh, sorry.
From Xinzhou, he asked, can we receive more than 3 base stations for positioning in the current indoor scenarios? I think it's yes.
Yes. So from measurements, it's no problem to receive the singles from 3 base stations in indoor, because currently for indoor scenarios, the inside distance is not large. Some typically is like in 3GPP, some is between the 10 to 20 meters. Also, this is this distance in practice. So normally we can have 3, 4. In our test beds, we can see 6 base stations to take the position. So should be no problem.
Yeah,
okay.
I would also like to. I would like to also add some comment to this. Usually, when we say base stations, we sometimes confuse with TRP. In typical case, even if they're from the same base station, even from the same cell, it is still possible that all those accessing points belong to the same cell, actually from the different position. So in this particular case, it is possible. Even under the same GNOB, there are multiple transmission points can be observed by the single UE. It's totally possible. And multiple GNOB, it is also possible. It depends on the deployment of the network. Thank you.
Professor Lee, you can continue.
All right, so yeah, I have a very generic question. It's about the indoor environment for positioning, because of if we use range measurement or use angle measurement, the most difficult thing is multipath and line of sight propagation. So what are your views for future, like a range-based or angle-based measurement for positioning purpose in this kind of very complex indoor environment?
So the question is, in complex environments of indoor, maybe your concern is not enough noise channels from the base station, right? So
you have to either deploy a lot of transmitters or get rid of the line of non-line of sight propagation, multipath impact as well.
Yeah. Firstly, is a non-line of sight, and we can use the algorithm as just mentioned. We have proposed algorithms in 3GPP and to identify whether it's north or unnorth. Actually, standards also include this synchrony, so that to deliver what's the actually we have the hard value and the soft value. Hard value is north or unnorth. Soft value is what's the probability to be north or unnorth. So that's more accurate. And this one can be realized so that we can remove some very bad receivers that's very close to unnorth, right? The second one is multipath. Multipath depends. If the reflection path is far away from the first path, actually the impact of the multipath is small. The worst case is if the reflection path is close to the first path of arrival, and it's quite hard to use like the music or correlation algorithm to distinguish the two paths. In that case, we have to get a very bad just estimation for the TOV or POV. That's a problem, yes. But I think in our just the presentation, our just the solution is to have the time domain just a window, so that after given the correlation spectrum or PDP, just the estimation, we can have a time domain and around the first pass, so that the reflection path away from the first pass can be cancelled in that case. But I think that's a very straightforward solution. Actually, there are many other solutions from the research. I think we should find some just like the interference cancellation from the papers. That's also okay. I think still have many solutions to solve the multipass, but I don't think we fully solve the problem in practice. Okay.
Thank you.
Thank you. Thank you, Dr. Wang. I think maybe you have many other questions, but we should end this session now because of time. Thank you, guys. Our opening ceremony will start 1:30, and we have 2 keynotes this afternoon. So thank you.
Thank you. Wonderful session. Thank you. Learned a lot.
Thank you.
Yeah.
See you this
Thank
afternoon.
you. Bye bye.
Okay, thank you. Bye.
Bye bye.